In our last video, we started talking about direct proofs. Let's see some more examples. So in that last video, we saw this particular example that I'd written 4 plus 3 equals 7, and I made the observation that I had an even number plus an odd number, and I got an odd number. And we proved that that was always true. What if we had 4 times 3? Well, now I get 12. So what it looks like is that I have an even times an odd, and I get an even. So let's prove that. So let's let m equals 2p, where p is from the set of integers, so it can be any integer. And we'll say n is equal to 2q plus 1, where q is also an integer. That's a z, sorry. And so therefore mn is equal to 2 times p times 2 times q plus 1, which is equal to 4pq plus 2p. I can factor out the 2 from these to get 2 times 2pq plus 1. All right, that's 4pq. This should be p. That's why I check. So 2p. This is an integer. Remember we talked about the axioms of integers, and so we have the product of 2 integers produce another integer, so that means 2 times p would be an integer, and that integer times q would be another integer. And when we add it to another integer, which is what p is, that would also be an integer. So this is the form of an even number, which is what we wanted. All right? Now what if we were to ask to do this? Prove that the product of 2 consecutive integers is even. That is, if the first number is k, then the integer after that should be k plus 1, and we want to show that that's even. Now, if we're clever enough, and actually I wasn't when I first thought about this problem, but we've actually already proven this. Here, we're making no restrictions that 4 and 3 be next to each other. I just happened to do that because that was what popped to my mind. But I could have done something like this. I could have said 4 times 7 equals 28. And it would still be an even times an odd, gave me an even. So what would these be? Well, if k is even, then k plus 1 has to be odd. If k was odd, then k plus 1 has to be even. So we've actually already proved this. This is really more of a special case because the numbers are forced to be 1 apart, but it doesn't change this underlying result. But let's say that I don't realize that, or we haven't already proven this. So the way I would approach this is this. I'd say, okay, there's 2 cases for what k is. Case 1 is that k is even. Okay? And therefore we have k is equal to 2p. And so k times k plus 1 is equal to 2p times 2p plus 1, which is 4p squared plus 2p, which is 2 times 2p squared plus p. 4p squared, 2p. Once again, this is an integer. And therefore, this whole thing is even. And then the other case would be k is odd. So k is equal to 2p plus 1. And this becomes k times k plus 1 is equal to 2p plus 1 times 2p plus 1 plus 1, which is 2p plus 1 times 2p plus 2. And this becomes 4p squared plus 4p plus 2p plus 2, And all these are multiples of 2 now. So 2 times 2p squared plus 2p plus 1p plus 1. And therefore this whole thing is even again. So this is the way I first approached this problem because I wasn't thinking of this. But if you're clever enough to realize, oh, we're just talking about an even times an odd, regardless of the order, right? Because once again, we have commutativity. So we could think of it either way. So if I didn't want to write it this way, I could just as well have written it as k minus 1 times k to get something like, 3 times 4. And this still could be 3 times 4. So the result still has to be even or odd, which of course we know it has to be even actually. Okay? Let's look at another example. If 2 integers a and b are each divisible by 3, then prove that their sum is divisible by 3. So what does this mean to be divisible by 3? That means that a divided by 3 is an integer, which we'll call p in this case. Okay? So what does it mean? Something like, 12 divided by 3 is 4. 30 divided by 3 is 10. But if I try 7 divided by 3, then I get 2 1/3, right? So I don't get an integer. So a divided by 3 is an integer, which is p. Likewise, if b is divisible by 3, then b divided by 3 is some integer, which we'll call q. So we want to prove that p plus q, a plus b divided by 3 is an integer. So how do we do that without knowing what a and b are? Well, remember we can factor this. So a plus b divided by 3 is equal to a over 3 plus b divided by 3, right? Because often you'll have this right here, and you'd combine those, say, well, they have a common denominator, so I get a plus b divided by 3. Well, we already said a divided by 3 is p, and b divided by 3 is q, and we said that each of these are integers. Therefore, their sum must be an integer, which proves that a plus b divided by 3 is an integer, and therefore a plus b is divisible by 3. Okay? Let me give you one last proof, or at least for direct proofs. And this is based on this summation. So there's a story that the mathematician Gauss, when he was a child, was in school. And the story says that the teacher wanted to keep him and the rest of his class busy. So they asked the teacher, said, produce this sum. 1 plus 2 plus 3 plus ... plus 99 plus 100. So this is the sum of the first 100 positive integers. And apparently, at least according to the story, Gauss came up with the answer very quickly. And why is that? Well, because Gauss was an extraordinary mathematician, and I guess also somewhat clever. He realized this. Let's take this right here. 1 plus 2 plus ... plus n minus 1 plus n is the sum of the first n positive integers. Now, how's that help me? Well, let's rewrite this sum, but in reverse order. So here we have n plus n minus 1 plus ... plus what would be here, 2 plus 1. And notice this. We have n sums, individual sums. This right here, this right here, and so forth. And what is each sum? Well, the first one is 1 plus n, which is n plus 1. And the second one is 2 plus n minus 1, which is n plus 1. If we wanted, we could do the next one, 3 plus n minus 2, which is n plus 1. So each sum, there's n sums total. Each sum is n plus 1, right? So the total product here is n times these n plus 1s, right? Because if the first sum was 5 and the second one was 5 and so forth, you say there's n 5s. Now what's the problem with stopping here? Well, the first row is the sum we want, but the second row is also the sum we want. So we actually have twice the sum we're trying to produce. So we divide this by 2. And therefore, what we have here is that this is I is equal to 1 to n of I times I plus 1, which is this sum right here. Okay? So that's 1 times, or excuse me, this right here would be this. First sum of I. So 1 through n, this is this right here. We'll see this again later because this becomes useful for some other things that we'll do, all right? And we'll also prove it again later using a different method because it's very common to use for that other method as inform and prove. But this also demonstrates that sometimes you have to be sort of clever to come up with proofs. And, most of us aren't often that clever, but you can get better at some of these things just by gaining more experience and also seeing how other people do things and sort of pick up on some little tricks. I hate to use the word tricks because it sounds like it's not legitimate, but it's really sort of the way of saying you have to be clever and realize certain relationships can be exploited to get the answer.